So, thanks all of you for coming. Today we are going to talk about clustering. And this clustering, first we need to know what is this and why we have to do this clustering. Nowadays, there are a lot of social networks, and even the normal websites are giving the ability to every single person on the earth to generate data. So everyone can generate data. So every day, every minute, every second, we are generating a lot of data. So we have some sort of solution for storing those things using the storage solution we already have. But the problem is how we can classify the data. The data is anonymous. We don't have any idea about those data. We need to find a way to just classify them, or better to say cluster them. And we cannot go manually inside the data and say, okay, we do it manually. I mean, the human cannot do it because the amount of data is a lot. It's huge, what we call it, the big data. So we have to ask the machine to do the clustering for us. And in order to do that, we have to guide the machine. It needs some guidance. I've been working on classification the last month. All of a sudden, Dr. Wu asked me to work on clustering. I didn't have any idea. I went home and just did a small search and found out, oh, the clustering is the same as classification. So what is the difference? In order to understand the difference, we have first to know a bit more about unsupervised learning and supervised learning. Let's say we have a bag of data, just a bag, imaginary. We have a bag of data. We don't have any idea about the data inside the bag. We pass it to a machine, we ask the machine to just group the data inside the bag. This is about unsupervised learning. How does it? How the machine does it? It looks for patterns. For example, let's say inside the bag we have millions of pictures of cats and dogs. So the machine does it like this. It checks the first image. It looks for some patterns. And so to find out that maybe this pattern, this color, it put it on. And again, it checks the next image and start to find for some pattern. Then after that, this goes on like this. So after a while, I mean the patterning, it can recognize the picture. Either this is a dog or this is a cat. So what we do in unsupervised learning is more about finding the patterns. And why we do care about the patterns? Because we want to find the groups, or better to say clusters. And on the other side, you have the supervised learning. In the supervised learning, we have to give some metadata about data ahead of the time to the machine. So we say to the machine, this picture is the picture of a dog, and this one is a cat, again. Another dog, another cat. And after a while, we can feed the machine with some test data. It's a test phase. And we can ask the machine whether this is a dog picture or a cat picture. And it can easily tell us which one is that. So, apparently, we can see here that this supervised learning needs to have some labeled data at the very first step. And we can see a pattern here. This clustering is responsible for labeling the data, and this one is responsible to classify the data. So we can use this one as a feeding system for the supervised learning. So this thing, we pass the raw data here, it clusters the data, and we pass it to this one, to supervised learning, and things are done. But there are just a few disadvantages to this system. For example, the supervised learning, the problem is the machine doesn't have any idea how many clusters we have in the data set. Is it 2, 3, 4? So when it doesn't have any data, there is two solutions. We can tell the machine how many clusters we are concerned about. Or maybe the machine does it itself, but maybe the result will not be the desired one that we want. So this is the problem about the unsupervised. And with supervised learning algorithm, there is another problem. And the problem is long-time training stage. Because we have to train the machine. We have to tell it, for example, this is a dog, this is a cat. But these are not ultimate dogs and cats. We have to show like thousands, millions to just improve the classifier. Here, sorry for the bad graphics, I just didn't do paint. These are some examples. Of course, these are ideal scenarios. We have blue balls here, red balls here. We consider these as two different clusters. So even with naked eyes, we can directly say that, okay, there is a regression line here that can separate these two clusters. So easily, anything above this line would be counted as a blue ball, and below that is a red ball. So when we feed the test data here, we put a point here, and we ask the machine, which one is this? The machine can easily tell us regarding this regression line that this is a blue bar. And we have a yellow star here, and we ask the machine and say, okay, this is the red star. But the question is, how we define this thing? It was a question for me. Okay, we have this data set here, but what is this here? Well, we're talking about dog and cats. Well, how we can put the dog or cat here? This is a feature space. A feature space. We define a set of features, and based on those features, the machine project the dog somewhere here, project the cat somewhere here. So based on those features, the machine defines which points here belongs to, for example, cat and dog. These are the ideal scenarios, but things are not always like this. Typical scenarios are like this. Maybe we have a cluster like this. Even for us, if there is a point here, we cannot say this is either a blue ball or red ball. But if you want to just take at the look at a more generic one, more typical one, unlike this. And we have separated and this top and bottom. But at the border there are some mixed up stuff. So if we draw a line, this regression line, we can see we have a red ball here and we have a blue ball here, and there is also a blue ball on the line itself. So we have some misclassified objects here, some data points. So if we want to have a better classification and better regression line, we would have a curve like this. But why we have something like this? These things happen because of overfitting. Maybe we have overfit the data a lot. So we have to do something known as cross-validation. What is a cross-validation? Let's say we already have here 100 blue balls and we have here 100 red balls. We try to change the scenario. We try to change our data set. So we said out of this 100 blue balls, we take 80. And the same year, we take out 80 as a new data set, and 20% as a test data set, as a test fitting. And we try to test it against the new data set and the new test data. So we get at the end an accuracy. We try this process many times, frequently. After a while, with different accuracy, we can say, okay, because this accuracy maybe is 95% or something like that, we say, okay, this one is better, so we choose this as our data set. We have different clustering algorithms under different categories: partition-based, hierarchical-based, density, grid-based, and model-based. These were completely new to me, and I roughly have any idea about them. For this knowledge sharing session, I decided to just cover these two. I covered these two, and each algorithm on each group I will cover in more detail. So first we need to talk about partition-based algorithm. So the definition is like it is covering the groupings in the data by optimizing a specific objective function and iteratively improving the quality of partitions. I will talk about more in this in detail. But there are just two criteria that have to be met. Each group must contain at least one object, and each object must belong to exactly one group. In order to understand this thing better, I try to describe the one algorithm that came in, one algorithm in this category. So let's say we have two different data sets, this one here and this one here. What we are trying to get is a regression line. We want to classify this data, and we need to find out the regression line. In order to do that, we just start like this. The k-mean algorithms first, and we need. I just need to say that the k means the number of clusters. So in this case, we define k as 2. So it becomes 2 means. So machine start by selecting two random ones. Of course, it's not random it can be optimized in many algorithms. But for our case, for the sake of simplicity, I just take point A here and point B here. After that, the point A says, okay, the guys are closer to me, come to me. And B says the same thing, closer to me, come to me. And after that, we have a line here. At this stage, you need to find out what is the center of mass here. So we have something here. We just add them together, divide them, we get something here. Just imagine this, okay? This is the center of mass. And on the other side, the B side, the center of mass is here. So we reset our data. In this case, this guy's A says, okay, the guy's closer will come to me, and B says the same thing. So we have our new line here. And again, we have to define center of mass. So here, we can say, okay, the data is more dense, so the A goes to B above. A comes here, and B comes down here. So, and after that, again, we'll repeat it. And the next stage, we can see our line becomes here, the center of mass goes there. I mean, it's defined with more precision, and center of mass here comes here. And finally, our regression line is the right one, we've been looking for, which comes here, and something like that. This is how k-means work. So it selects two initial points, and based on the distance of the other data points and the center of mass, it's defined this line, regression line. This k of n, which is k nearest neighbor, is not related to clustering. It's related to classification, not just it's one slide, so I decided to talk about it because it's related. So in our case, let's say we have our data clustered here. It's red balls here, blue balls here. And at the very first case, we have 3 points, I mean 3 new data. We want to find out this is what, and this is what, and this is what, and we don't have the regression line. So the k nearest neighbors, as its name implies, the k is number of neighbors. It gives us the result based on the nearest data point. So here, the nearest data point is this one. So it says, in this case, it's a 1. We define k as 1. We say, okay, this is the blue one. And in this case, it's okay, this one nearest is like this, because this, no. But in this case, we are trying to check this algorithm with k as 3, taking k as 3. Normally, we take the k as an odd number because we want to run a voting system. For example, in this case, the nearest one to this new data point is red. But in fact, this one is in this space, so it might be blue. So how we can do it, we say, okay, we calculated 3 distances from this one. Distance is easy, just the square root of delta x and a square plus delta y square. This is simply calculated. Of course, in the 2-dimensional space, it could be 3 more, whatever you want. And okay, it says these 2 guys are neighbors, and this one is neighbor. So, but because these 2 guys are voting for me, I take it as blue. So this is KN, super easy. But it is for classification. It doesn't have anything to do with this plus cluster.
Before you go further, I'd like to add to the k-means. Go back to k-means. So what's the problem with k-means? Do you know? What is the weakness of k-means?
If we don't have a data with the right density, maybe we cannot define the right regression line.
Okay, the problem with k-means is the k is unlimited. You do not know where to start. You need to start with k or 2 or 3 or 4 or 5 or whatever.
You mentioned that clustering is a problem of clustering.
Yeah, so now you easily define as 2 clusters.
It's imaginary.
Yeah, I'm just saying that the weakness of k-means is the k. How we determine the k? Okay, the k is one of the problems. Then what is the weakness of k then? How about k then? K-nearest neighbor. Do you know what's the weakness?
Weakness of KNN. We connect where the data is right cluster.
Actually, the complexity will grow when the data set is large. Because every single point have to go and connect, find the nearest neighbor to every single point out there, n-1 point. So it's exponential. So when you have more data set, every single point will be, you need to calculate the distance, then it will be very slow.
Yes.
So KNN is not very good for big data set.
Yes. The next category of clustering is hierarchical based algorithm. So data are organized in a hierarchical manner depending on the medium of proximity. What we mean by proximity is the distance between the data points. So I will tell you later on how it works. A datagram represents a data set and tracking the progress. Of course, apart from the cluster, we have a datagram that is just useful for us as humans to just see how the process is going on. And we have, okay, it's better to start with the algorithm. Okay. This is a hierarchical agglomerative clustering. But before this, I would like to say something. Okay, this algorithm, this hierarchical algorithm have two types. The one is bottom to up, which is agglomerative, and the other one is top to bottom, which is called divising. So this one is agglomerative, which is bottom to top, and I'm going to talk about. So initial states are like this. This algorithm is a single algorithm for categorizing data into groups. Start by measuring the distance between two groups. This is what we know as the similarity factor. This is very important, and later on I will talk about this one. But just what we need to know is just the distance between two clusters. We know it as the similarity factor. And the other one, we can initialize the algorithm by creating a separate cluster for each data point, so there will be total n clusters at the beginning. It says like this: if we have a data set like m data point in that, at the very first stage, we take every data point as a cluster. We treat it like that. And then compute the cluster distance scored between all pairs of clusters, and this is its time, m squared by n, and we can sort the result, because it will optimize the algorithm. So if we calculate the distance between all the data nodes in the data set, and we want to later on do it again, well, it will take a lot of process. We can just store it somewhere and sort it. So it will improve and optimize the algorithm. The next step is finding the closest pair and merge them together to just make a bigger cluster. And this process already will be continued until we have a desired number of cluster, or just everything, all the clusters merge together and become one big cluster. So things start like this. We have our data set like this at the very first stage. What we need to do is just need to calculate the distance between every pair of clusters. And after that, we need to know that we take every single data point as a different cluster. This is the first step. Okay, at the very first step, the algorithm finds the nearest clusters and it tries to merge them. This is what is happening in the algorithm, and for us to just understand what is going on, there is something called a dendrogram that really shows what's happening there. It says, okay, these two clusters are joining, and the height of this shape here just define the distance between these two clusters. So the first iteration, the first closest pair are found. We go next to the second pair, second closest pair, and we find it here, and we have defined a dendrogram there. And as we can see, the height of this one is more, but the distance between these two are more than the distance between these two. And okay, in the previous step, we found two clusters. Now again, when we want to repeat the process and find the closest cluster, these two are counted as one cluster. and also these two are counted as one cluster. So each merge reduces the total number of clusters by 1. So these points were not into this cluster, but at this point, this stage, because these two were so close, they put it all into one cluster. So we can see here, this alone, this lonely data point here is trying to get merged with this one that we had it from the previous stage. So we have this thing, and the height is more than this. It's because the distance between these two are more than these two. It's standard of that. And finally, we will end up with something like this. We have a cluster here, a cluster here, and a cluster here. But in this case, in the clustering, it's a problem. We do not know how many clusters we want. There is a threshold. In this case, we have defined that I want 3 or 4 clusters. And because we said something like that, the algorithm stops at this stage. But if we do not define how many clusters we need, the algorithm will continue to the point that all of these things will go into one cluster. This is what would happen if we do not define what is the desired number of clusters that we are interested in. So here we have 4 clusters. 1, 2, and this is a dendrogram. And actually, if you want to see how we can stop it, there is a cut line here. In the next slide, I will show it to you. In the dendrogram, there is a line here that says, okay, this line is trying to cut everything. So this one is here, so it becomes one cluster. Cut this one is here, it becomes another cluster. It cuts here, becomes another. So we can say, okay, 1, 2, 3, 4. We have at this stage, if we try to stop the algorithm at this stage, we will have 4 different clusters. But if we don't stop it here, we can go and merge them all together. Okay, this has been my slide. I finished it so fast. I tried to cover 2 different categories. Category of the clustering, partitioning, and hierarchical-based algorithm. And I will try to just cover the rest, which are grid and density algorithm, categories in my next round. And just one thing, I forgot this thing. As you remember, I talked about the similarity factor at the very first of this algorithm. And I said, okay, the similarity is very important. We have something here. When we have 2 clusters, here, the distance between the nearest data point of these 2 clusters are called single leakage. We use this term later on. And we have something else in here. We have 2 clusters, and the distance between the most far points in these 2 clusters are called complete leakage. And we have mean leakage and we have central leakage. So now why we use this? In this slide, you can see here we have 2 different clusters. This one has used the single leakage, and the other one has used the complete leakage. So as we can see here, the single leakage has been more successful here to define this cluster here. So we can say if the distance between the data nodes are not that far, they're close to each other, the single leakage, at this point you see here, this is successful because we have this in here. Otherwise, we will put this one into this cluster. But here, it tries to find the nearest node, and you put it in the same cluster. But in here, it's using the complete linkage, and instead of combining this with this, it tries to combine this with this, because the basis of this one is to combine with the more far points. This works in this scenario better for single leakage. But if you want to talk about this one, single leakage will not work about this one. And you take all of this thing as one cluster, which is not, we are interested in 5 clusters. But this single leakage doesn't work here. And here, this complete linkage will yield a better solution, I mean better result. And yes, this is the end of this session.
I want to ask, how do you apply hierarchical clustering to a document? In what sense do you measure the distance between documents? How?
Between documents. Okay.
Because the tree method you are talking about is actually for the paper, and the clustering for document data set document. So we will talk about K-mean, KNN, and hierarchical clustering. So how do you define similarity for document? For example, K-mean. Okay, let's start with K-mean.
Oh, okay. You mean
because you want to cluster document according to.
Yes, I mentioned that thing, and said that we have something called feature space. But we need to project the document into these things. So we, in the case of documents, we need to say, okay, we are maybe interested in this set of words.
So what is the features for a document? If the features for a picture, we have pixel, color, intensity. There's so many features. So what is the features for document?
What is the feature?
So what do you think is the features of a document?
Okay, if we are interested to find the topics, okay, we may say, okay, this series of words, if you can see the series of words is related to the computer science. This series of words, if you can see that these are related to the nature. And we can define these things, or maybe a series of, you know, if you use Twitter, the people are using some shortcut and some abbreviation for words. For example, best regard, they use just PR. We can define this thing in the back and we say, okay, these are the features. Or maybe we can say the punctuation, these are the features. And we can define these features and just project our documents into these graphs. Right? Or is punctuation used?
Yes, not very clear. Is punctuation used? Are you sure?
Yes. This is a feature. Everything is a feature.
No. I was hoping that you have read the paper, you understand how the paper classified it, and
the paper is so abstract. You say, okay, KNN,
no,
one paragraph, done.
Yeah, because the paper is actually a survey paper. Okay, it's a survey paper. Let me explain. So it's a survey paper means he actually tried to write a lot of what people have done. Okay, so let's say he said there's a survey of how people use K-mean. So it will be a link of a paper that you refer to. You should go and refer to that paper.
Now, in the next session, I want to wrap everything up. So I bring up the things in the paper. But for now, I had to bring them something in order to give some understanding about what is clustering.
You don't need to start every time from a presentation from ground up.
But because I had to understand it, I really didn't have any idea what is clustering.
Yeah, like now you have 1 hour. So you will talk about the basic 3 techniques today: the K-mean, the KNN, the hierarchical clustering. You have another 30 minutes to go. Actually, you can say how you apply this.
Because I want here, I bring to the table to say, okay, they have shared this. This is the result. This is the result.
So for a reminder, next round, we don't need to be teaching like primary school because we are postgraduate students. We don't need to start from ground up. It's more about how to apply the algorithm. I want to see more that kind of knowledge sharing. Because we are not lecturer, we are not coming here say this is KNN 101, we will learn about KNN. It's more about how to apply the technique, what is the recent technique. We want to also discuss what is the weaknesses, what is the strength, why are people using this technique. That is more, that is the next sharing that I'm looking at.
For the next paper, I will go exactly like the paper.
Yeah. Any other questions? But do you understand what I'm trying to say?
Yes. We said we have a limited time, better to just share.
No, I mean what is the features that you want to?
Now, for me, these things were new, but I know I understand totally what you're trying to say. I have to spend more time on that and bring some more stuff on it.
Because this is exactly what the master is doing. You know? Finding, if you can classify the document, then you can actually find the topics. He's actually doing topic classification for people. Doing that. Topic classification. No, he's actually exploring what techniques. So there are many techniques out there, like.
I have checked the risk, I have checked the greed, I have checked the density, I have checked the risk, but I'm not ready to describe them, but I checked almost the 5 categories there.
Yeah, those are clustering. What Dr. Su is saying is there's a method like how to find similarity, like LDA. Have you heard LDA? Yeah.
That is, you just go for topic modeling with this in RDA.
You mean EM? Or it's just another thing other than the
Yeah, it's actually finding similarity.
So every time I come here, you just throw at me some new terms, so I have to learn it.
You just started, right?
No, yes, I just started.
So that's the process.
Yeah, that's a process.
No, before this, I was.
You ask everybody here, we are learning.
I mean, it's okay, but just give me the idea, I have to go there.
No, I'm not saying that you must be expert. Want to explore it, find out about it, see what is it all about. I'm not saying tomorrow you're going to come and write a paper, no, we get the result, whatever, no. But there are things that people have done. I'm just saying that now, today the presentation is no depth.
Yeah.
That's very superficial. It should be more depth, because 2 weeks already.
I did other things. This thing, I just did it for 3 days.
Yeah, so 2 weeks got 14 days, so
I
just
developed an application you asked me to do.
Okay, then you should demo the application next time. Do you have
This is a knowledge sharing. I'm not supposed to bring it.
No, you can show everything. It's not about just.
I was not
you have your pre-concept of what is knowledge sharing. It's not correct.
It's like 3 days ago, I sent you this one and said which one you want me to work on. So I just.
Yeah, but I did tell you we can actually did demo on that. Remember?
Oh yes, I have it. I have it ready, but you just asked me to complete that.
No, what I'm saying now
is
the knowledge sharing is just not just knowledge sharing. It's also research progress update. And sooner or later, all the other postgraduates also they update. At the same time, you also sharing. You update what you have done, and you read a paper. You just share with us what you have done, or what your progress, or I found a new technique. I want to demo. That would be. Any other question?
I have one suggestion.
Question.
Suggestion. The K means FCM, everything we almost know. Okay. So if anything new, you encounter anything, maybe you can know that one. You get it, my points? Because the K means are all introduced very old. Even I think the professor of Dr. True himself knows that one. Yeah, I know. It's a very old technique. Yeah, still the persons are using that one. Yeah, even I also used when I came here as a PhD student first.
So I started something, and I'm trying to build up the rest of that. And I'm sure in the next 2 or 3 sessions that I will have here, it will go so much behind it. So this was just a start. I mean, just was a start. And this is actually not my field of expertise. I have no idea what this is. What is this? And last time I was looking for it. What is this factor? What is that factor? I have no idea what that is. My field is software. It doesn't have anything to do with this stuff.
So anyhow, you are already here in this field.
No, yes.
So hereafter, you should not say this one.
I'm just telling you that I will be improving. I will be improving. This was just.
We want that proving only. So that's what Dr. also said. Okay. So the thing is, just try to come up with new one and try to analyze that one completely.
Yeah, sure.
Because when we are asking some features, we are not able to in a good question to say what is the features in document something product has, right? So we want specification of that one, so that we can understand something else other than that what we know. Okay, so we want something more.
Okay,
because we definitely all of us. He's also PhD man, PhD. He already finished his masters, So by research, so he knows better than me as well. So we want something more. That's it. Yes. There are many things in K-means itself. Even though the K-means is still not there, it is in bloom. Why? You can give some explanation for that one. Even though there is a negation, some negative points over K-means, still persons are using that one. So you can give some points of the positiveness of that one, so that we can take that point and we can try to do in our research maybe, or we can help you to do that one.
Yes, time will help us to just find
Yeah.
out those points. Yeah.
Okay, thank you. Anyone want to present next week?
So this is your turn. Give me the new point. This is your turn.
Yeah,
Mr. Yen, Dr. Yen can present. What's the topic?
Introduction. Introducing Microsoft Analytics Services for Taxonomy.
Really?
No, it's not that. Not that one. Is that one for this Saturday? But next Wednesday I'll do it.
Okay.
I'll do demo.